Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. Let us continue our lectures about curve sketching, and let us here also talk about, consider three different examples. Let us start by this function y equals ln 4 minus x squared. What is the domain? Well, you need to remember that this is the graph of y equals to ln x, and ln x has a vertical asymptote uh, x equals to 0. Uh, so the domain of len from 0 to infinity, x has to be positive. What is inside len has to be positive. So 4 minus x squared has to be positive. It cannot be even 0 because len 0 is not defined. Actually, when x approaches 0 from the right, len approaches negative infinity. So how to solve this inequality? Well, we find the zeros of 4 minus x squared, and the zeros of 4 minus x squared are negative 2 and 2. If you put x squared minus equals to 4, if you take x squared to the other side, then x would be plus or minus 2. There are two solutions of this equation. And the sign between the two roots is opposite to the sign of x squared. So it's positive here. If you replace by 0, you notice that it is positive, negative here, and we need it to be positive. So the domain of this function is from negative to 2. That's very important because then the graph, when we graph this function, the graph would be between negative 2 and 2. We don't know yet what would happen at negative 2 and 2, but this is end. These two numbers represent an end of the interval. So we have to discuss what happens at these ends of the interval. I have to see what is the limit when x approaches negative 2. I cannot approach negative 2 from the left, but I can approach it from the right for len 4 minus x squared. Well, when I approach negative 2 from the right, this means that I replace x by negative 1.9. So this would be this 4 minus x squared. When x approaches negative 2 from the right, 4 minus x squared will approach 0 from the right. And len 0 from the right, when x approaches 0 from the right, len goes to negative infinity. So actually the limit here is negative infinity because of the graph of len. Notice that limit len x when x approaches 0 from the right is negative infinity. Also, when I approach len 4 minus x squared now from the left of 2, because I cannot approach 2 from the right because the domain is between negative 2 and 2. So I replace 2 again by 1.9, and this again will go to 0 plus, and len 0 plus is negative infinity. So when the graph, this means that I have two vertical asymptotes. X equals to negative 2 is a vertical asymptote, and x equals to 2 is also a vertical asymptote because the limit goes to negative infinity. So when when x approaches 2 from the right, the graph goes to negative infinity, approaching negative 2, approaching 2 from the left, and negative 2 from the right. Also, the graph goes to negative infinity. That's valuable information. Okay. Domain. What about x-intercepts or y-intercepts? Are there x-intercepts or y-intercepts? Let me start by the y-intercept. Y-intercept, put x0, so len 4. So len 4 is the y-intercept. So there is a point 0, and len 4. The graph passes by this point. Well, len 4 is 1.4, approximately 1.4. So this is the y-intercept. If this is 1, this is 2, this is the y-intercept. Okay, so the graph passes by this point. What about the x-intercepts? Well, to find the x-intercepts, I put y0. So I need to solve this equation, len 4 minus x squared equals to 0. And to solve this equation, I raise both sides to the base e. And you need to remember that e to the power len x is just x, because ex and len x are inverses of each other. So I will have 4 minus x squared equals e to the power 0, and e to the power 0 is 1. So when I take x squared to the other side, it would be positive, and bringing 1 here, it would be 3. So x squared is 3. So x is positive and negative square root of 3. So these are the two x-intercepts. So I have two x-intercepts, 1.7 and 0, and negative 1.7 and 0. So it seems that the graph passes by these points. So I expect that the graph is like this according to all the information I have up to now. Just need to make it more accurate. Okay. Okay. I hope this would be okay. I even don't like it. Sorry, I'll do it again. Okay, I think this is okay. Two x-intercepts, two y-intercepts. It approaches the asymptotes and it goes to negative infinity from the left of 2 and the right of negative 2. These are all the informations up to now. Is there a horizontal asymptote? Can I find the limit when x approaches infinity? Or the limit when x approaches negative infinity? I can't, because x does not go to negative infinity or to infinity. X is only between negative 2 and 2. So there are no no horizontal asymptotes. Symmetry. Is the graph symmetric? What is f of negative x? Well, I have len 4 minus x squared. So if I replace x by negative x squared is just x squared. So actually this is f of x, so the function is even. And the graph is symmetric about the y-axis, which is the case. Good. So all the information is now no contradiction between them. What else? Asymptotes, intercepts, domain, good. Symmetry. So now we go to the first derivative. What is the derivative of len? If you remember, derivative of len u is 1 over u, this is chain rule, times the derivative of u. Derivative of 4 minus x squared is negative 2x. So this is the first derivative. Now, the first derivative does not exist when x squared is 4, when x is negative 2 and 2, but they do not belong to the domain. So the first derivative is 0 when negative 2x is 0 or when x is 0. So the only critical number is 0. Well, what happens at 0 then? Let us use the first derivative test. What is the sign of f prime here to the right of 0 and to the left of 0? And you can say that we are not going to negative infinity and infinity here. We are really discussing just from negative 2 to 2 because that's the domain. And 2 and negative 2 are just not included in the domain. So between 0 and 2, if I replace x by 1, 4 minus 1, negative 2, this is negative. Negative 1 will make this positive. So this is positive. So the function is increasing here, decreasing here, and at 0, I have a local maximum. So the local maximum would be f of 0. And f of 0 is 1.4. It is the y-intercept. So, or len 4, okay? So the point 0 and 1.4, this point is a local maximum. Good. So this agrees with our graph here. And it's increasing really to the left of 0 and decreasing to the right of 0. That's excellent. So let us see the information from f double prime. Well, f double prime, I will use the quotient formula. So 4 minus x squared to the power 2. And now, what is the derivative of the denominator? It is negative 2 times 4 minus x squared minus negative 2x. So I can write it positive 2x times the derivative of 4 minus x squared, which is negative 2x. Is there any common factor? It is only 2. Okay. I can take negative 2 as a common factor. So I'll have 4 minus x squared. And I took negative 2 as a common factor. So I have positive 2x squared. If you want, you can expand as usual if you like doing that. So f double prime is actually negative 2 times 4 minus plus x squared. Well, x squared plus 4 is always positive, and negative 2 negative. So in fact, if double prime is always negative, because here it is squared, the denominator is always positive, the numerator is always negative, because this is 4 plus x squared. So if double prime is always negative, so f is concave down in the domain from negative 2 to 2, which is the case. And no inflection points because concavity does not change. So that's the graph. And I just, if you want to make it more accurate, please check what happens at half 1. Okay, it's even. You can just replace half 1, 1.5, for example, and complete the graph, make it more accurate. But this is an acceptable graph for this function. The next example, it is just a polynomial. So the domain or real numbers. So no vertical asymptotes. Let us find x-intercepts. Y-intercept is easy. The y-intercept, if I replace x by 0, so the y-intercept is 0. And to find the x-intercepts, I need to solve this equation. 1 over 5 x to the power 5 minus 8 over 3 x cubed plus 16x equals to 0. And to solve this equation, I can multiply by 15 to get rid of 5 and 3. So I will have 15 over 5, that's 3. 15 over 3, that's 5. 5 times 8 is 40. And 15 times 16 is 240. And now I can take x as a common factor. I'll have 3x to the power 4, 40x squared plus 240. And I can solve this equation. This is a quadratic in form equation. So I can solve it using the quadratic formula for x squared, okay? Or I can try to find b squared minus 4ac, which is the discriminant. So b squared, to make sure that there are solutions or not, b squared is 1,600 minus 4 times 3 times 240. And this is 2880. So this is less than 0. So this polynomial has no real zeros. It's either positive or negative. Well, it is positive because if I replace x by 0, I have positive 240. So this is always positive, but it's multiplied by x. So the only x-intercept here is when x is 0. And if I put x 0, I get y 0. So the graph passes by the point 0, 0. It is the x-intercept and it is the y-intercept. What else? The horizontal asymptotes. There is no horizontal asymptote because this is a polynomial, but let us find limit x approaches infinity of y. To find the limit when x approaches infinity, we take the term with the highest power, which is 1 over 5, x to the power 5. And x to the power infinity, if I replace x by infinity, infinity to the power 5 over 5 is just infinity. While limit y when x approaches negative infinity, also I take the highest power. But now when I replace x by negative infinity to the power 5 is negative infinity over 5, that's negative infinity. So this means that no horizontal asymptotes, okay, no horizontal asymptotes, but I know the end behavior of the graph, okay. I know that up to now, the graph passes by the point 0, 0. And these are the information. And when x goes to infinity, it goes to infinity. So here it goes to infinity. And here it goes to negative infinity. And no vertical asymptotes. Yeah, and the domain or real numbers, and the intercept is 0. These are all the informations we got up to now. Symmetry, let us check f of negative x. Well, f of negative x would be 1 over 5 negative x to the power 5 negative 8 over 3 negative x to the power 3 and 16 times negative x. And this is actually now negative 1 to the power 5 is negative, so it's negative 1 over 5 x to the power 5. Also negative to the power 3 is negative, so it'd be positive 8 over 3x cubed and negative 16x. And this is in fact negative f of x. If I multiply f of x or y by negative, I will get this one. So this function is odd. And the graph is symmetric about the origin. That's good. So if we have the graph in the first quadrant, we will know the graph in the third quadrant by symmetry. All right. Now we can talk about y prime, the first derivative. Well, y prime is 5 times 1 over 5, that's 1, x to the power 4, minus 3 times 8 over 3, that's minus 8, x to the power 2 plus 16. This is also a quadratic in form equation, and you can notice that x to the power 4 has a root, which is x squared, and 16 has a root, which is 4, and the sign in the middle is negative. And if I multiply 4 times x squared times 2, I get 8. So these three terms makes a perfect square. So in fact, y prime is written like this. And this is x squared minus 4. I can write it x minus 2 times x plus 2. So I have x minus 2 to the power 2 times x plus 2 to the power 2. It's clear that y prime is squared, so it's always positive. Y prime is always greater than or equal to 0. It could be 0 when x is 2 or when x is negative 2. So critical numbers, what are the critical numbers here? I have critical numbers at 2 and at negative 2. So at 2 and negative 2, I have critical numbers, but y prime is always positive. So y is increasing. Y is increasing. On the interval from negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. Okay, you can say it's always increasing, but at negative 2 and 2, we have critical numbers. This means that no extreme values, because the function does not change from increasing to decreasing. And this means that we have horizontal tangent at horizontal tangent lines at x equals 2 and x equals negative 2, because the derivative is 0. So the slope of the line there is 0. So no extremes, but at 2, whatever, let us find 2 and what? Yeah, let us find these points, negative 2 and f of negative 2 and 2 and f of negative 2. If I replace 1 over 5 times 2 to the power 5 minus 8 over 3 times 2 to the power 3, which is 8. Okay, let me write here multiplication. Plus 16 times 2, that's 32. 256 over 15. So this is 256 over 15. And you know that the function is odd. So I'll have here negative 256 over 15. And this number is approximately 17.1. So this is negative 17.1 and this is 17.1. So if I say that this is 5, 10, 15, so here, okay, I have a horizontal tangent, and here 5, 15, so 5, 10, 15, 17. So I have here also, this is 1 and this is 2. I have also here a horizontal tangent, okay, at these 2 points. So I can say that yeah, it may go like this here, and it will go to infinity, so it may go like this here. And we will see that it is always increasing. It's increasing here, it's increasing there. That's good. Now let us find y double prime. So y double prime, I find it from here. So it's 4x to the power 3 minus 16x, that's at plus 0. Okay, if I take 4x as a common factor, I'll have x squared minus 4. So it's 4x times x minus 2 times x plus 2. And the zeros now of f or y double prime, I have negative 2 and 0 and 2. There are 3 zeros of f double prime. Let us y double prime. Let us check the sign. All of these zeros are zeros of multiplicity 1. Okay, so if you go back to X section 4.3, you will understand how I find the signs here. I'll choose, for example, 3. If I replace x by 3, positive, 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 so it's positive here. So it would be negative here, positive here, and negative here immediately because each 0 has multiplicity 1. But you can check, for example, replacing 1. If you replace 1, it would be negative, and so on. So here it is concave down, concave up, concave down, concave up, and I have 3 inflection points. So 0, 0 is an inflection point. Negative 2 and negative 17.1 is an inflection point. 2 and 17.1 is an inflection point. So 0, 0 is an inflection point. Okay, let me start from negative infinity. From negative infinity to negative 2, so up to here, it's concave down. That's good. Now, from negative 2 to 0, it's concave up. So here, it will start to be concave up like this. Okay, try to make it concave up. Okay. Let me do it again. Here, notice we have concave up, and then it's concave down, and then it goes up like this. Notice we have a horizontal tangent at 2 and negative 2, and this is concave up, concave down. So we have 3 inflection points, 0, 0, 2, and negative 2. So this would be the graph of this function. You may choose more points at 1, at 1.5, negative 1, negative 1.5, 3, 4 to make an accurate graph, but this is acceptable. I have a rational function. All right. I need really to understand the function. I need to factor. If I take x as a common factor, I have 1 minus x here. And factoring this is x squared minus 3x plus 2. So I think x minus 2 times x minus 1. Yeah, negative 2. Yes, that's the factored form. Notice we have 1 minus x and x minus 1. Can I cancel these two? And the answer is yes, you can, but you need to, the answer is negative 1. If you divide these two, the answer is negative 1. So remember that a minus b over b minus a is just negative 1 because the difference between them is a sign. So y would be negative x over x minus 2, but I have to mention that x cannot be 1 because if x is 1, y will not be defined because I have x minus 1 in the denominator. It's true that I canceled these two, but I cannot replace x by 1 in the function. So if I ask you what is the domain of the function, the domain would be all real numbers except I have problem with 2 and I also have problem with 1. So if I ask you what is the difference between this function and the original function, these two functions are exactly the same, but they differ at 1 because this function is defined at 1 while the original function is not defined at 1. So when I write x not equal to 1, they would be exactly the same. So the graph, what do we have at 1 then? You remember, if 1 is a 0 of the denominator and the numerator together, we will have a whole at x equals 1. It is not a vertical asymptote, but we will have a vertical asymptote at x equals to 2 because 2 is a 0 of the denominator and it's not a 0 of the numerator. And the 0 of the numerator is 0, so x equals to 0 is an x-intercept because this is the 0 of the numerator. And the y-intercept, if I put x0, I'll have 0, so the point 0, 0 is there. So I have a hole at x1, 0, 0, and a vertical asymptote at x equals 2. Let me find the horizontal asymptote. And of course, I'll deal with this function. I'll graph this function, okay, where x is not equal to 1. So what is the limit when x approaches to infinity of negative x over x minus 2? If I take as usual, it will not be here, doesn't make a difference to talk about infinity or negative infinity. In both cases, I'll take the highest power up, the highest power down, and x cancels with x. So I get negative 1. So y equals to negative 1 is a horizontal asymptote, and the graph approaches negative 1 from the right when x goes to infinity and when x goes to negative infinity. So this is a lot of information. Let me put it here, or at least when you put the information like this, step by step, maybe you make it easier for yourself. X equals to 2 is a vertical asymptote. At x equals to 1 is a hole. Well, if I replace x by 1 here, okay, what would I get? Negative 1 over 1 minus 2. So negative 1 over negative 1. That's 1. So here, this function passes by 1 and 1, but it shouldn't be equal. 1 shouldn't be equal to 1. So 1 and 1, I have a hole. Okay. So at 1, 1, I have a hole. Notice that 0, 0, the function passes by 0, 0. So it looks like, and what about the horizontal asymptote? Y equals to negative 1 is a horizontal asymptote. This is a horizontal asymptote. It looks like the function is going like this. It should approach the asymptote, it should pass by like this, the hole, and it should go, it approaches also the horizontal asymptote. So this would be the graph of this function. Only the circle is not really, and it should be like this. Okay. This is the graph. This is the graph of the function up to now, putting all of this information that I have. Okay. So it is not defined at 2, and it's not defined at 1. At 1, there is a hole. At 2, there is a vertical asymptote. Good. All the information now is okay. And let us symmetry. It's clear that the function is not symmetric, but if you find f of negative x, just for understanding, if I replace x, and I'm dealing with this one again, if I replace x by negative x, so I'll have negative x over negative x minus 2, and this would be x over negative x minus 2. And this is not f of x, and it is not negative f of x, because negative f of x, you multiply either the numerator by negative, so it would be like this, or the denominator by negative. So I'll have negative x plus 2. So negative f of x could be this one or this one. These two are equal. If you multiply the numerator and the denominator by negative 1, you will get this one. So 2 over 3 is negative 2 over negative 3. That's no problem with that. And both of these two does not equal to x over negative x minus 2. So the function is neither. Okay, good. Let us now start finding the derivative. Where is f? This is f. Okay, the derivative, I'll use the quotient rule. So x minus 2 to the power 2. The derivative of the numerator is negative 1 times the denominator minus the numerator, which is negative x, so this would be positive x, times the derivative of x minus 2, which is 1. So just 1. No need to write it. So negative x plus x, this will be cancelled. And negative times negative, it would be 2 over x minus 2 to the power 2. This is f prime. It has no zeros because the numerator has no zeros, but it is does not exist when x is 2, and 2 does not belong to the domain. So no critical numbers. There are no critical numbers for this function. So no extreme values. Yeah, there is no maximum, no minimum. This agrees with us. And you can see that f prime is always positive. This is positive and this is square positive. So f is increasing on the domain of f. So yeah, the function is increasing. This agrees with our graph here. That's excellent. Now let us try to find f double prime. And to find f double prime, I notice that this is 2, so I'm going to find this rule. The derivative of 1 over u is negative u prime over u square. So the derivative would be negative. What is u prime? The 2 is there. Okay, this 2 is a number, so it's there. What is the derivative of u? It is 2 times x minus 2 to the power 1 times 1, the derivative of x minus 2. So this is negative u prime times 2, the number here, over u square. So I have x minus 2 to the power 4. And I can cancel x minus 2 with x minus 2 to the power 4. So I'll have negative 4 over x minus 2 to the power 3. And you can notice that if double prime does not exist at 2, but 2 is not in the domain, and negative 4 is always negative. But at 2, it is not in the domain, but what would be the sign of f double prime? Because this is power 3. If I choose 0, for example, 0, then it would be positive because this is negative, negative over negative is positive. If I choose 3, it would be negative. Okay, so there is concavity. Let me check something. F prime, this is negative u prime. 2 times x minus 2 times 1. Yeah, that's correct. But here, why it is negative? Derivative of 1 over u square times, yeah, there is no negative in the formula. Sorry. Derivative of, yeah, it is derivative of 1 over u is negative 1 over u square times the derivative. Yeah, that's correct. Good. So x minus 2 to the power 4 and negative 2, that's correct. So f double prime is negative. But this can't be because to the right of 2, yeah, still there is a part of the graph to the right of 2. Yeah, that's good. So it's up, it is here and down. Still there is a part here to the right of 2. We did not, yeah, I did not graph that part. So now it is no inflection point, of course. Everything is okay. No inflection points because 2 is not defined. Before 2, concave up, that's accurate. After 2, it's concave down. So here, it's concave down, okay? Now the graph here must be like this. It's concave down, and it's increasing, okay? Notice y prime is always increasing. It's increasing. Of course, it cannot be here. There is no graph here because there is one x-intercept only, which is 0, 0. There is no x-intercept here, okay? So it has to be like this. There is no graph here, of course, because there is only one y-intercept and then it's not a function, okay? So this is the correct graph of the function and it agrees with all the information. To the right of 2, it is concave down. The function is always increasing, no critical numbers, no inflection points. There is a hole here, there is vertical asymptotes. Yeah, but maybe we did not do one thing, yeah, one thing. What is that thing? We wrote that x equals to 2 is a vertical asymptote, but we did not find the limit when x approaches 2 from the right. and from the left. Since 2 is a vertical asymptote, you remember we should always find this limit. So what would happen if I replace 2 by 2.1? This would be positive, this would be negative. So when you approach 2 from the right, the graph goes to negative infinity. Yeah, now I am sure of my graph, okay? And what is the limit when x approaches 2 from the left? Okay. From the left, 1.9, this would be negative, this would be negative, it will go to infinity. So when I approach 2 from the left, it goes to infinity. Yes. So this is what was missing. When I did not find this limit, I hesitated how to continue the graph. Okay, but I should have found this from the beginning to see how the graph approaches the vertical asymptote. So now the graph, I'm 100% sure that it's accurate and everything is fine. Well, we solved how many? 1, 2, 3. So that's enough. I'll stop here and I will continue the last 3 examples in another video.